Flat Earthers put forward one of their finest warriors, Mr Flatzoid FE, who was armed with a triangle, and he has done battle with me on several occasions, although each time he's been put on his arse.
Well, first of all, welcome everybody to the video that's going to show this, how can I put it, egghead. He's just that, ignoramic egghead who is very, very dedicated to his cult belief, even when shown wrong, cannot concede, and then just digs his hole deeper.
The shame of it is, he doesn't seem to realise that, and he kept getting up again, just to be knocked down all over again.
Can anyone say delusional? It's not me the one that's claiming not triangles while showing triangles.
Unfortunately, this flat earth fanatic is too stupid to know when he has been beaten. He got frustrated and started accusing me left, right and centre of lying. He started accusing me of being dishonest.
Nah, not accusations, mate. It's fact. You are a dishonest, non-conceding coward who just can't take his ego out of the picture and just be humble and say, listen here, I was wrong. You do use triangles and it is triangulation. Even though I show you this, you tell me I'm wrong, and then you show me the same thing. So yes, I would stick to that. You are dishonest and you are a liar, especially because you like leaving out very critical parts that are specifically put to you.
So the battle went back and forth, with Flatzoid somehow believing that you can calculate the lengths of the sides of a triangle when you only have the angles.
Already validating my claim that you're a liar. Please show me stating exactly that. Mr. Sensible? Come on, I'll wait for that. Let's see if you can actually back up your claim.
Here is the challenge I made.
With a sextant, you are using triangulations. You have an A, B and C. The 90 degree from the zenith and your angle towards the luminary. Triangulation.
Flatzoid, because you have a triangle on the screen doesn't mean it's triangulation. With triangulation, you need angles to several known positions. All you have on the screen is a triangle. With this, you're not even solving a triangle. Let's see what information you've got.
And again, one showing you're ignorant, telling me you cannot use a triangle to triangulate, and you told me you cannot even figure out this triangle using a single triangle, which I did show you. You know where you left this information out for everybody?
One triangle.
Right, where do I start with how wrong you actually are? First of all, triangulation requires you to be able to figure out something based on the angle. What do you think A is? It's the angle to the luminary. That is triangulation based. Now, Mr. Sensible, you've taken that, let's say, 45 degree angle to B. You have the time that you took it to there. So you look in the almanac and now you see, it is 5 p.m. I see this star and this with this amount of degrees. So obviously the circle of equal altitude based on the time the star is seen from this angle, let's say is 900 to 1,000 miles away from me. You have just debunked your own self, telling me you cannot triangulate with one triangle. Mr. Sensible, what do you have to say for yourself? Now, if you want to be more accurate, you can do more than one observation and therefore do more and more until you get your exact pinpoint location, aka triangulation, done with one triangle.
You've got your viewing angle, the angle of the star above your horizontal at A. Let's say it's 45 degrees. You have B, the position of the star. Directly below it, you have its GP at C, which is 90 degrees to the horizontal. So what have we got? We've got 45 degrees to the star, 90 degrees at point C. We don't know how far it is from A to C because that's the distance we're trying to work out.
No shit, Sherlock. That's why a luminary has its geographic position, so you know on a map where it is from you.
Working out the distance with a triangle, Mr. Sensitive.
We don't know how far it is from A to B to the star. We don't know how far it is from B to C, the height of the star. So basically we have no sides of the triangle.
No sides of the triangle. Let's see. 45 degrees from your viewing point to the luminary. Luminary has 90 degrees to you. You know that is geographical position is situated on a certain part of the map, like latitude and longitude, and it has a circle of equal altitude. You can only see that star from that position at that distance. Can you count to 2? 1 plus 1 makes 2. Distance?
So go ahead, solve that triangle and give us length A to C. You can't.
Yes, just according to you. And apparently everybody can see now just how ignorant you are if you don't even know how to work out a single triangle.
You do not have the information. That is a total fail. And even if you did, that's not triangulation. That's just solving one triangle.
And yet, after you said you cannot do it, I did it. And just in case, because you don't actually know and understand, in case he does it, then it's not triangulation. But everybody seems to see you are ignoring this that I posted, remember?
Using triangulation.
Sextant. A sextant is a navigational instrument that uses a telescope and an angular scale to calculate the latitude and longitude. Making a measurement with a sextant is called sighting the object or taking a sight. The optical instruments called sextants have been used as navigation aids for centuries, especially by seafarers. The sextant replaced the astrolabe, which was used in ancient astronomers for navigation. And its simplest form, a sextant consists of an eyepiece and an angular scale called the arc, fitted with an arm to mark the degrees. By manipulating this part, a user can measure the angular distance between the celestial bodies. Remember that keyword, angular distance. Usually Earth and either the Sun or the Moon. The observer can thereby calculate his or her position of latitude by using a trigonometric operation known as triangulation. Whoa! The word sextant derives from a Latin term for 1/6 of a circle, or 60th degree. This term applied to generally be a variety of instruments today, regardless of the spans of their arcs.
Despite telling Flatzoid on numerous occasions that you can't do that it's a mathematical impossibility, despite numerous people in the comments of his videos explaining to him how it's impossible.
Wait, are you serious? I haven't seen anybody actually explaining anything other than
My globe, because globe.
That's the usual rhetoric of the people that defend the globe.
Because globes cannot work, no?
He holds on to that belief. I even told him to try using an online triangle calculator.
You did? Okay, I must have missed it. Well, just in case, would you be so kind as to provide where you told me to use this online calculator?
Flatzoid, let's have a quick look at one now. Here we go.
Mr. Sensible, something doesn't make sense here. I thought you said the trigonometry doesn't use right triangles, so why are you trying to show me a right triangle calculator?
A right angle triangle calculator. It comes preloaded with some lengths for sides, so we'll get rid of those because we don't know them.
You see, Mr. Sensible, this is where your ignorance really shines bright. This shows that you guys do not do proper research or even attempt to be, how can I put it, honest if you do know this information. When you set sail, you do know what a DR is, correct? That would be your distance and bearing. Usually you have that before you even pick up the sextant to do your measured angle. That is how you're going to get your GP and your distance from that GP. Thank you, Mr. Sensible. You keep showing over and over again. You are just nothing more than an ignoramus and a charlatan, because somehow your gullible followers just keep eating up all the nonsense you spew, even while we show things like this, that you simply do not understand basic navigation.
Right, angle alpha is our star's elevation from the horizon. Let's pop this in, it's 50 degrees. We've got 90 degrees to the zenith, and angle beta would have to be 40, making up a triangle. Let's see if we can calculate length B. cannot calculate based on two angles only. Oh dear, Flatzoid. Oh dear indeed. To any reasonable person, that really should have been the end of it. But not to a flat earther such as Flatzoid. I still kept explaining to him how it's impossible, and he said this: "So you keep doubling down. I will do one final quick video with one triangle, with just one triangle. You sure do need to re-look at your priorities."
Yes, and I stand by this comment, Mr. Sensible. I made a final video on it, but since you keep pestering me, I thought, let's make a nice premiere for everyone to see just how ignorant you really are.
So I replied, "Okay, a final video from you. Please show how you work out the distance, length of sides, for your triangle. Angle of star elevation at 40 degrees. Apparently, you can calculate the distance from the observer to the GP. You have the three angles now, 40 to the star, 90 at the GP, and you would then get 50 at the star, which is nonsense, of course, as that would mean that the star is local, but that would be the third angle in your triangle. You don't need to know what the GP is, so you don't need to look it up. I can tell you immediately, without solving a triangle, how far the observer is from the GP, as I am using a sphere. You claim to be able to get it with a triangle. Please do."
How many times do we have to explain this to you guys? Your baseline is a flat horizontal 180. You do not have a sphere underneath your measurement. You are using triangulation with a triangle on a flat base. Your dip angle is literally just your elevation from the surface of the water. That is why when you evoke your artificial horizon, you are just shooting yourself in the foot, because that just shows you do not need a sphere, you do not need dip correction, you just need a flat baseline to be able to triangulate your position with a 90-degree right angle, which you said doesn't work that way, even though everything we show you is with it.
So Flatzoid had previously claimed that he had shown me this several times, but this was going to be it. The final battle of the war. He would produce one video that shows me how he could do it. He produced a video, and this video is so stupid that obviously logic has failed.
So you do know you call him the same guy that's done navigation and is a glober stupid and illogical because he shows how triangulation works with a triangle?
And so now I have to bust him with cheese. Let's see his video.
I see a star here, okay, and I recognize that star. I just know that particular star in the sky is star A. I'm just going to give it a name, star A.
Hold on a second, Flatzoid. That's not your voice. You've actually used somebody else's video.
Wow, way to state the obvious.
Duh.
You see, I got sick of showing you how I did it, so I decided let's get a glober to show you how it's done.
Still, I suppose if it actually does show us how you can calculate the sides of a triangle using only the angles, I guess that's good enough. Go ahead.
Okay, and let's also suppose that right now the time is 6 p.m. Okay?
Now once again, I don't want to appear churlish, but one does feel a chill coming on. I don't recall in my maths lessons, when being taught how to calculate triangles, that it's dependent on the time of day.
And this is exactly why I will not ever use you for navigation. With navigation, time and date is very important, because you're using things that move with time and date. You know, they got cycles over the sky.
Now, if somebody out there is watching this video and actually knows how to celestial navigate...
Well, that counts out any flat earthers then, doesn't it?
That seems like a bit of a statement out of bigotry, don't you think?
Clearly I'm going to be oversimplifying, but I think for most everybody you'll get the basics of what I'm talking about. And that's the whole purpose of the video.
Well, you may well simplify it, but I've got a feeling that for flat earthers, it's still going to be well beyond their grasp.
It seems to me the only time you have anything to say is ad hom and bigotry. When will you actually bring any constructive arguments to the table?
Alright, so here I am, I'm out in the middle of the ocean, I see star A, okay, I know it's star A, and it's 6 p.m. Now, from my location, okay, I see star A, let's say, at 50 degrees above the horizon. Now, how would I get that measurement?
Oh, I know, a sextant.
So the way I would get that measurement is using a nautical instrument. You've probably seen it. I'm going to try to sketch it real quick. It's called a sextant. Okay, it looks like this. You've probably seen mariners using it. And what they do, they pick this thing up, they look through it, and then they kind of swing something back and forth, and it's able to tell them the angle of an object above the horizon.
Yes, this is simplified. They pick up the sextant and swing something back and forth.
I really do have to be very specific with these measurements. Okay, so anyways, I take my sextant out. I know it's 6 p.m. and I look at star A and I'm seeing at 50 degrees above the horizon at 6 p.m.
Okay, yeah, he should have actually already had his DR set and his time with date. And yes, then you pick up the sextant, because you cannot have an angular measurement without your flat base and having the rest of the information required for the triangle to work
on this particular day. Alright, so what does this mean? Okay, if I have those two pieces of information, I'm on my way to finding my position at sea.
Well, Flatzoid, I see you said enough information to find your position, so I presume we're about to see how you can calculate the sides of the triangle. Now you only know a couple of angles.
That is incorrect. You do not only know a couple of angles. Remember, I told you first have to set your DR, so you know your location bearing and the distance traveled already. See, this is the problem you guys have. You guys don't think everything right through. You just try and see, this is the argument against me, so I must try and do something to obfuscate from the problem, so they would think I'm right and you are wrong, kind of thing.
Well, there is a book that navigators use, okay, and oh boy, if I'm not mistaken, I think the book is called like HO 229. It's kind of a weird name for a book. It's been a long time, but anyways, it's essentially a reference of all these stars that we look at, these primary stars that we use for navigation.
Flatzoid, why would you have to look at a nautical almanac to solve a triangle?
This is on par with Simon and Dan's question. Why do phones not fall upwards but downwards? You know, it's idiotic to even ask such a question. You are navigating using triangulation. You need to know the GP so you can have your distance. This is what I'm saying. You are ignoring all the information given to you just so you can try and make a point that you do not use triangles. In matter of fact, you do use triangles and you triangulate. It's been shown to you time and time again. So just stop being such an idiot and just concede that you were wrong.
As this is celestial navigation, I know straight away, with that star's elevation at 50 degrees, it's 40 off the zenith, times it by 60. That means I am 2,400 nautical miles from the GP of the star.
Do you see the problem here? 2 minutes ago you said you do not use the triangle. Now you're explaining angles in a triangle and saying, because sphere, I know distance.
I haven't looked it up in an almanac, and I haven't solved a triangle.
And I go to this book and I'm saying, okay, it's 6 p.m. and I'm looking at star A. And the book will tell me, well, star A should be located at this position, okay, at 6 p.m. Okay, at 6 p.m. you should be seeing star A directly over your head, 90 degrees, right? So if I'm standing out here in the middle of the ocean at this position, okay, not where I'm at, okay, at this particular position, I would see star A directly above my head at 90 degrees.
Do you know what this means? This means the 90 degree from the GP to your zenith, which is also 90 degree, is a flat baseline.
Well, I'm still failing to see exactly how you are solving a triangle here, Flatzoid. But perhaps you're keeping your powder dry and it's going to be a sneak attack and you're going to get me from behind.
Nah, mate. I'm not a coward. I do it face to face and mano to mano. And, well, kind of shown you to be just an ignorant fool.
We'll soon see.
Okay, so hopefully that makes sense to you, right? So if I'm right here and I'm looking at star A, I would be looking straight up, right above my head up in the sky. But obviously, at 6 p.m., I'm looking at star A and I see it at 50 degrees in the sky, not 90 degrees, not above my head. So with those two pieces of information, okay, I can use some trigonometry. Okay, this is going to be a right angle. I have a degree here. I have a location here. And I'm not going to get into the math because that's not the purpose of this video.
Well, Flatzoid, the purpose of your response video was supposed to be to show us how you can calculate the sides of a triangle when you only know the angles.
Weird. You're making arguments for me. Like I said, show me where I said you only need the angles, Mr. Sensible. Please, I'm waiting because you've still not yet provided me with this statement I made.
Still, in this example, we do have 90 degrees at the GP, 50 degrees at the observer, and therefore 40 at the star. So, go ahead, solve the triangle.
But essentially, what you're able to do, what the book is able to do, is to say, listen, if you're seeing star A at 50 degrees, okay, and not at 90 degrees, well, the only way you can do that is that you have to be a certain distance away.
Right, this is it.
Did you actually listen to what he said? He said, according to the GP, you will have to know the distance because it can only be seen a certain distance according to the GP on a map.
We're going to find out. How do you calculate that distance?
Maybe you're hard of hearing or you have some memory loss. He did tell you he's not going to show the calculations. He's literally just going to show you how the navigation works with right angle triangles.
The way you can do that is that you have to be a certain distance away from its location at 6 p.m. Okay, and it's basically going to build us a little circle here. So let's just make a number up.
What?
Say that again.
Let's just make a number up. Let's say in order to see star A at 50 degrees, okay, at 6 p.m. at night, you have to be 900 miles away to be able to see that observation. Okay?
He's making it up as he goes along. No, I'm not.
So that's it, Flatzoid. Some basic introduction to celestial navigation where the presenter makes up the distance in miles, not even nautical miles, when he could have just used the distance, the correct distance of 2,400 nautical miles.
Do you ever listen to yourself back? Do you ever see your actual contradictions? How can you tell me it's not using triangulation with angles and you can't get a distance, yet you give a distance based on your triangles, and then you go out and have a problem because he didn't say nautical miles and because he made up a distance? If that is the level of rebuttal, then I have no hope for you.
So your example video doesn't even show us how we can calculate a distance, let alone how that distance is calculated based just on 3 angles of a triangle. Now fear not, siblings, you may think that Flatzoid's being stupid, but believe me, the stupid goes much deeper than that. Let's have a look at that guy's YouTube channel for this video. Here we go, let's have a look. Celestial Navigation Math. The channel is Tablet Class Math. Special note, the Earth is round, oval. So my use of right triangles is a simple math model to explain the basic concepts of navigating by the stars. However, the actual math needed to perform celestial navigation involves trigonometry on a sphere. You complete gimboid.
If you just actually knew, he changed his description box after people started moaning about it. You know, because the people like yourself have religious views that just don't comport with how the navigation works. So he actually had to go and change it to say, oh, by the way, it is a globe because I believe in a globe. And I just have to point out to you, if it wasn't the correct math, right angles on a flat base, he wouldn't be using it in the first instance. He would actually have deleted this video and actually done the correct spherical math. But no. You know why? Because the spherical geometry comes after the flat baseline angle measurement. Whoopsie!
Zaphod, what do you think about this?
Yeah, okay, so 10 out of 10 for style, but minus several million for good thinking, huh?
But no, the stupid didn't stop there, did it, Flatzoid? Because you did a quick follow-up video with just a few slides. Let us see just how well you do understand.
Ah, yes. Soon I will be having the reaction video out for this, because clearly you guys do not understand what you're reading.
The first slide is some brief information about sextants, and you say, read it through a couple of times. Well, if only you had, Flatzoid.
And I rest my case. You do not understand? Why? Because instead of telling me what's going on, you say, "Oh, Flatzoid, you don't understand, and you simply have not read it." But the weird thing is, I'm the one who posted the video, so obviously I read what I posted, Mr. Sensible. So maybe I should go through it and explain it to you? Is that what you want? Okay. How to use a sextant. The sextant is a complex device, but luckily it is very easy to use. Basically, a sextant measures the angle between two objects. Oh, Mr. Sensible, do you understand? Measures the angles? Anyway, with at least one being celestial. That would be the sun or star, you know, or moon. Remember, never look directly at the sun. No, duh. I don't think anybody's going to be that simple, but with the amount of globe trolls and their arguments, I wouldn't be surprised why they had to actually put that in. Anyway, the user looks through an eyepiece and after adjustments sees both objects superimposed on each other. This measurement of the angle is then taken through the use of two mirrors. Okay, so what did we take out of that first paragraph? Very simple. It's a complex device. Check one. Very easy to use. So basically anybody can use it if you just have an understanding of it. Okay. Thirdly, what does it do? A sextant measures the angles between two objects. What would those two objects be? Well, lucky for us, there's a diagram on the side. Would that be the sun and the horizon? And finally in this paragraph, we see that you'll have to adjust the two objects together, to superimpose them together, to get the two mirrors to line up properly. Yep, even this alone, it shows it has to be parallel or the angle's not going to work. With your curve, you're not going to have a parallel. Okay, on to paragraph number 2. The user looks through the sextant's eyepiece directly at the first object, usually the horizon. Yes, because that will be your base. There is actually a mirror in the line of sight, but because it's only partially silver, the user can see beyond it to the horizon. Well, that's partially correct and not, because you get two types of mirrors to look through. Anyway, there is actually a mirror in the line of sight, but because it is only partially silver, the user can see beyond it to the horizon. The other mirror is connected to the movable arm and directs light from the second object, usually the sun or moon, and reflects it into the half-silvered mirror. The movable arm is adjusted until you can see both the first objects, the horizon, and the second object, the sun or moon. Then you read the measurement of the angle located on the movable arm. This was just simply trying to explain to you how it works with the mirrors and how you have to align them together to get your angular measurement. Third paragraph. The most common way of using a sextant is to measure the angle between the horizon and the sun. By knowing this angle and your local time, you can determine what your latitude is. If you also know the Greenwich Mean Time, GMT, you can also determine your longitude. Now this is very important, Mr. Sensible, especially for you. Do you understand what was read in this third paragraph? Do you know that because you measured an angle between the horizon and the sun, by knowing this angle and your local time, you can determine what your latitude is? That's already a point on your map, you know. And also know the Greenwich Mean Time, which is GMT. That helps because, you know, it's determined from Greenwich Mean Time. You can determine your longitude. Now you have a latitude and longitude on a map using a triangle measured with a triangulation. Do you understand what was read here, Mr. Sensible?
The next slide has a vocabulary list including trigonometry, the mathematical relationships between the sides and the angles of triangles. oh dear.
Oh dearie dear, you got me. No, Mr. Sensible. Just by you reading this out shows how stupid you are. And I'm going to say it again. You are stupid. Okay? This document is teaching people how to use a sextant for celestial navigation. And it's inside there. Why? Because you get the sides of a triangle. Whoopsie. Okay, let's move on to the actual document now. There are many things you can determine from a sextant, but we will use it to determine your latitude for this exercise. Follow the steps below to use the sextant. 1. Do this exactly at noon, when the sun is at the highest point during the day. Look through the eyepiece. Adjust the angle of the sextant until you see the horizon. Number 4. Now adjust the movable arm until you see the sun, because you should never look directly at the sun. The sextant has a number of filters that will block out most of the sun's light, but will let enough through to see it. Make sure to always use the filters that you do not hurt your eyes. Number 5. Adjust the arm until the sun rests just on the horizon. Number 6. Now measure the altitude of the sun by reading the angle on the movable arm. Number 7. Write down the exact local time. I think that's quite self-explanatory. I don't think I need to go through what everything is. Just them showing you a sextant can be used to determine a few things, but yeah, it's quite simple. Let's move on. Optional for determining longitude. Write down the exact GMT. This gives you all the information you need to find your latitude and longitude. Knowing that the measurement was taken when the sun was at the highest point in time, you know that it was noon. This and the angle of the sun off of the horizon can tell you your latitude. If you also did step 7, which is write down the exact local time, you could determine your longitude. Knowing the GMT time and the time where you are tells you the difference in the time between your location and Greenwich, England, which is 0 degrees longitude. You can relate this time difference to the distance and find your longitude. To actually compute your latitude and longitude, you need to do a number of long calculations, another way that computers can help. Yes, so this is just explaining to you, by measuring it, you get your latitude and your longitude. Something that Mr. Sensible seems to not understand. You know, kind of pinpointing your position on a map, and then they're just saying, yeah, computers just make it easier because it's a number of long calculations that you need to do. Lesson vocabulary list. Geometry, the mathematical relationship for points, lines, angles, surfaces, and solids. Yes, because you're doing geometry. Trigonometry, the mathematical relationships between the sides and the angles of the triangles. I wonder why they would mention this if you're not using trigonometry and triangles, Mr. Sensible. A sextant, a navigational instrument containing a graduated 60-degree arc, used for measuring the altitude of celestial bodies to determine the latitude and longitude. Accuracy, a measure of how close the data comes to the correct answer. Precision, a measure of how close the data points are relative to each other. In other words, how well grouped the data is set. Computer, a programmable device to process information. Equation, a statement usually written as symbols that are separated into left and right sides and joined by an equal sign. Altitude, the angle between 2 points. For example, the angle between the horizon on the ground and the sun. Very important, the angle. You know, the one you're measuring between the luminary and the horizon. So yes, flat horizontal base.
The next slide has the formula for solving triangles. For instance, for angle A, the sine of angle A equals the opposite over the hypotenuse. For B, you've got the tan of B is the opposite over the adjacent. Read it through a couple of times, Flatzoid. You need the lengths of some sides in order to solve a triangle.
Don't you find it really odd that, Mr. Sensible, you keep pointing to me about trigonometry and triangles, but your argument is you do not do trigonometry with celestial navigation and sextant, or use triangles? Anyway, back to educating you. Trigonometry review. Trigonometry is a branch of mathematics dealing with the relationships of the angles and the sides of triangles. So in other words, if you're doing trigonometry, you require triangles, Mr. Sensible. The three basic trigonomic relations that we are concerned with here are sine, cosine, and tangent, abbreviated as sin, cos, and tan, obviously. They are ratios of the length of the two sides in a particular triangle. The particular type of triangle that is most useful in mathematics is the right triangle, which has one angle equal to 90 degrees. Ooh, this is a definition of killing you guys. By definition, the 90-degree angle is made by two lines that are perpendicular to each other, like the corner of a square. And third side of the triangle is made by a sloping line connecting the two perpendicular lines. This sloping line is called a hypotenuse, and the name comes from the Greek hypo, meaning under, and I hope I'm saying this right, tenein, meaning to stretch. It is easiest to show this visually. So you see, Mr. Sensible, you're definitely going to be using triangulation and trigonometry with triangles for using celestial navigation for a sextant.
The final slide shows dip correction. It shows the sextant with a horizontal, that dotted line, but the dip down to the horizon is shown. In this case, 0.0413 degrees. So when you take your reading, you get a measurement of 20. You have to deduct the dip, giving you a corrected angle of 19.959. I think you need to show Oakley and 10th Man and all those other dimwits. Perhaps this bit isn't too advanced for you. Draw a picture of a navigator in the boat. Oh, I hope you haven't eaten all your crayons.
Yes, okay, I understand. Your projection is noted, because at the end of the day, that's all you actually got. You don't have an argument. All you do is just showing you have nothing but ad hom and attack because you are shown wrong. So yes, the dip horizon is not because of a curve, Mr. Sensible. It's literally just because you are higher than the ocean, the horizontal. You know, because you need a flat base to be able to do your trigonometry. So, in other words, to do that, you have to minus your eye level from your reading so you can get your eyes to the bottom. Full stop. It's got nothing to do with a curve, got nothing to do with a heck, it can be a donut shape or a donkey shape. At the end of the day, that dip is just your elevation as your eyes are above the horizontal plane. Set base flat.
Let's see if you understood what you read. Well, Flatzoid, I don't think you have.
Nah, the problem is you don't think at all. Proven by, we just went through the whole document and we can clearly see who's the ones who understand the documents and who doesn't.
Well, I think we've all waited long enough. Flatzoid, gird your loins because you are about to get busted with cheese.
Busted with cheese. Okay, this should be interesting. Let's have a look.
So here is our science demonstration area, lovingly framed with cheese triangles.
Sorry, did you just say science? I thought I heard you say science.
First thing we want is a triangle. Oh, I think we may need to do some work on that. So, we have our triangle.
Okay, a triangle of cheese. Still not seeing the science here, Mr. Sensible.
A, B and C. So, how do we work out this distance? Well, if we've got this angle here, which is 40, the sine of the opposite over the hypotenuse, or the cosine of the adjacent over the... We don't know anything.
That's a physical block of cheese. You can easily take a ruler and measure it, then you would know all the angles and sides, but still fail to see the science. Where's your IV and DV? Where's your hypothesis? Not making sense.
we cannot calculate it. But thanks to Flatzoid's video, we now stand a chance. What we do is we check our clock. 6 p.m. That means that this is 900 miles long.
Ah, I see. You think a block of cheese is the same as celestial navigation trigonometry. Sorry. False equivalence.
Well, let's check that length.
Using a ruler is hardly the same as measuring angular distance, you know, with a sextant, Mr. Sensible. Might want to figure that out.
Well, it appears to me to be 10.5 centimetres, Flatzoid, and not 900 miles. You idiot.
Yes, you really should stop looking in the mirror when you say that, because just now you're actually going to start believing yourself.
Well, since we've got this view to our star with the angle of 40 degrees, what about other observers? Let's ask Alice. She's further away. She sees the star at 20 degrees. Do you see a problem here, Flatzoid? Well, let's ask Bob. He's at a different distance. He sees it at 30 degrees. Yep, a definite problem. This is why using the elevation of stars on a flat Earth won't work, because the height of the star would have to change dependent on your distance from it.
First off, that's a straw man argument. None of us have ever claimed that the stars and luminaries are physical objects, you know? I can debunk this very easily. Have you ever tried to measure the altitude of a rainbow, Mr. Sensible? It's apparent to many locations at different vantage points. But can you actually measure the height of it, Mr. Sensible?
Chuff nuggets. So having shown you how things just can't work with triangles on a flat Earth.
No, you just shown you don't have a clue how optics works. But that's old news.
Let's have a look how it really works. Let's start off with a sun. Well, we could make it a bit more cheesy. Right, here is our sun. Excellent. Do you know what? I think I prefer if we looked at a star.
But that's not how stars look. Every time you guys show us stars, it's some gaseous ball of gas in a second law of thermodynamic violation vacuum.
Cool. Now, let's put that star over the Earth.
Whoa, so you're first really assuming straight away it's a sphere. You know, you don't even have a radius to have that sphere. Remember the black swan? I know you don't understand the argument, but it debunks your radius.
Excellent. What we need now, of course, is a flat earther. Meet Flatzoid, well, Parmezoid. Let's stand him just here, wanting to know exactly where he is by using celestial navigation. Now, in reality, a star is a very long way away.
Oh boy, you should not be called Mr. Sensible. You should more be called Mr. Illogical. You see that star, you see that line to the plate? That is a zenith, according to your globe model. And then, if you have me, the Flatzoid, why is the zenith pointing in a different angle? Would that have a new, different zenith? A different geographical position? Makes me think of something I showed you before. Oh wait, here it is.
The zenith is not the GP.
The zenith points out the GP, as you have a zenith on top and a nadir, which is in the bottom. You know, when you move your GP, then you have a new zenith and a new nadir. So yes, your zenith is definitely pointing your GP.
The GP is the point on Earth directly below your zenith. An extremely long way away. So let's move this star about, I don't know, 20 light years away off the screen. So the star's light hits us in parallel lines.
Again, you're assuming the distance to the stars. Again, assuming it's so far, light rays have to be parallel, while you ignore the inverse square law of light. Very exciting news.
There's the line down to the GP. There's the light from the star down to Parmezoid's location. So now Parmezoid wishes to take a reading with the elevation of that star. That star is 50 degrees above his horizon.
I think the best way to say this is...
Any evidence you can have a curved adjacent when acquiring an elevation angle?
Is that an optical angle or a geometric one?
Optical angle. You mean acquiring sight of a star with a tool to measure something geometrically.
Which means it's 40 degrees off of his zenith. 40 times 60 means that this point is 2,400 minutes of arc around a curve.
Remember when I asked you why you multiply by 60? It was exactly for this reason, Mr. Sensible. Do you realize that an arc, you are measuring angular distance?
That is his distance. That is how you get the distance to the GP. You are not solving any triangles.
Not gonna go through this again. We've all seen. You have absolutely bugger all to know what you're talking about.
Whatsoever. Now the really interesting thing, Flatzoid, which is gonna bake your noodle, is we have established that Parmesoid is 2,400 nautical miles from the GP. That's 2,761.871 miles on the Earth. If you were doing this on the Moon, it would be 2,400 nautical miles, but it wouldn't be that same distance in miles.
Wonder why that would be. Ever thought of that? Maybe because it's not physical?
Doing it on a plate, it's still 2,400 nautical miles, but only about 8 or 9 centimetres. The conversion is different. It's always 2,400 nautical miles for the star, 50 degrees above the horizontal, 40 degrees off your zenith, because it's a measurement around a curve. So, Mr. Flatzoid, do you get it yet? Do you not see why you failed? Do you not see why you don't use triangles? So, Arnold, what are you doing? Arnold, Arnie, leave him alone. No, that's Flatzoid. That's a flat earther. What are you going to do? Arnold, are you biting his leg off? Look, that was a very expensive piece of Parmesan cheese. You're ruining my experiment. Do you not see why you don't use triangles? So, Arnold, what are you doing?